So good afternoon, everybody. It is my pleasure, instead of Gabi's today, to introduce our speaker, Dr. Dominik Brunner. Dominik is the head of the Atmospheric Modeling and Remote Sensing Group at the Empa in Switzerland. He got his PhD from ETH in Zurich, then worked had a postdoc at KNMI in the Netherlands, went back to ETH in Zurich as a research assistant before he became the head of the modeling group in 2006. And it's a pleasure to welcome him today to talk about Lagrangian transport and inversion emission modeling of non-CO2 greenhouse gases in Europe.
So thank you, Christoph. So it's nice to be kind of invited by my former PhD student, and it's a great pleasure to be here. and Louisa, yeah, we've met many years ago. Yeah, it's a. So the last time I've been in Boulder was 17 years ago, and it's a great pleasure to be back here again. And well, the topic of my presentation here, I will focus on Lagrangian modeling, and I have been told that there's not a lot of people doing Lagrangian modeling here, so that might be interesting for you to learn a little bit about the type of modeling we are doing. And you can see here a picture of Jungfraujoch, which is the station where a lot of the measurements that I'm going to use in this presentation have been made. And I would like to particularly thank also my collaborators, Stefan Henne, Christoph Keller, Stefan Reimann, Rebecca Hiller, Martin Vollmer, who did part of the measurements, the data analysis. Yeah. So I thought before going to my presentation, I briefly introduce Empa, which might not be so well known to you. So Empa is actually within the ETH domain. So all the governmental or Swiss federal research institutes and universities are organized under the umbrella of this ETH domain. So that's our minister and then the head of the ETH domain board. And then you see here ETHZ, which is the ETH in Zurich, EPFL, which is the counterpart in the western part of Switzerland, so the ETH in Lausanne. And then there are 4 research institutes associated: the Paul Scherrer Institute, WSL, EAWAG, and Empa as one of them. And there you see our director, Gianluca Bona. So just a few numbers about Empa. We have 3 sites in Dübendorf. That's the main site, St. Gallen, Thun. And we have 28 laboratories, 950 employees, so it's quite large. And I think an interesting number, or impressive number, is this 140 PhD students, because 10 years ago we had only 5. And so we have completely turned from something like a service and testing facility into a research institute over the last 10 years or so. And, well, the other numbers are not that interesting. So our own lab has especially historically done a lot of measurements. So more or less at the beginning of our lab was the call for setting up a measurement network for air quality, air pollution monitoring within Switzerland, and Empa, our lab, has received the duty to do that. So we are running 16 measurement stations over Switzerland. So the National Air Pollution Monitoring Network is run by our lab. We are also strongly involved in WMO GAW activities, so the Global Atmosphere Watch. So we are running the World Calibration Center for ozone, CO, CO2, methane. And so we send out our experts to the different global sites of the GAW network to do calibrations and make sure that everywhere the same things are measured on the same scales, hopefully. And so my duty here is I do modeling, and we do Eulerian modeling and Lagrangian modeling, and I will only speak about this Lagrangian modeling work. And we are also doing a lot of interesting instrument development. So we are building, for instance, these GCMS Medusa systems, which are used in the A-gauge network, and we are, as far as I know, currently the only group that's building these instruments. And we also do a lot of laser technology, quantum cascade laser instruments for isotope measurements, CO2 isotope, methane isotopes, N2O isotopes, anything you can dream of. So this talk will be about, so it's organized as follows. I will briefly introduce the Lagrangian concept and the type of model that we are using, and then show you how we use these Lagrangian models to estimate the sources of halogenated hydrocarbons over Europe, then also an application to airborne methane observations, and finally I briefly present the project CarboCount, which I will actually present tomorrow at the NOAA meeting in more detail. So if you're missing some details today, go to the NOAA meeting. So Lagrangian dispersion modeling. So as you certainly all know, within the Lagrangian framework, you're moving, the frame of reference is moving with the mean flow. And the main problem with this Lagrangian concept is that if you start off with, let's say, a regular volume of air, it will be distorted by the flow, by the shear, and so on. And you also have turbulent diffusion, so the information, maybe the molecules that have been initially contained in your volume, will spread out, and you get dispersion. And to deal with these problems, there have been different ways of formulating Lagrangian models, and this is from a recent publication by John Lin, 2012. And so this is kind of a classical trajectory model where you treat an air parcel like a solid material that would not deform or anything. It's just like a point in the atmosphere that is moving with the flow. Then another classical thing is box models, so especially chemical box models, which you transport along trajectory, and as the air is moving up and down, the volume gets compressed so that the mass is always conserved within the box. So very idealized and not very realistic over long transport times. Then there have been ideas how to deal with the dispersion of Lagrangian models. So there have been Gaussian puff models. So you treat a release of a species of a compound as a puff, which then flows along the mean flow, but at the same time spreads in the form of a Gaussian plume. These models have problems with dealing with shear in the flow. They are not very good in that. So there have been attempts to solve that problem by puff splitting and merging schemes, rather complicated. And here the last class of models is Lagrangian Particle Dispersion Model, where instead of a single trajectory, you simulate air particles, which are infinitesimally small air parcels, and you simulate a lot of them, and each one is following a different turbulent path. And if you want to learn more about Lagrangian models, I warmly recommend to read or buy this book, which has just appeared as the AGU monograph series, and was an outcome of the Chapman conference we had in 2012 in Switzerland. So, and also that figure is out of that book. So Lagrangian particle dispersion model is just briefly say a few words about that. So we typically simulate a very large number of air parcels, infinitesimally small, so like points in the flow. And so with that, we simulate dispersing plumes. We can simulate either forward or backward in time. And so we consider the transport with the mean flow, U, but also the turbulent component, the U dash, so the deviations from the mean flow, and convection. And the turbulent part is usually simulated with a Langevin equation. So what you see here is the change in the wind component, for instance, the vertical wind component over the time step dt. And it has a deterministic part and a random part. And this here is, as you can see, it's proportional to minus W itself over a time scale tau. So this is like a damping term. So if you have a turbulent motion upwards, for instance, this one would damp this upward motion with a time scale tau, which is the Lagrangian time scale. And so it's like a viscosity term. And this is really adaptive from Brownian motion. And this is the random term. So this d theta is a random number that you pick from a Gaussian random distribution with a standard deviation of 1. And this is scaled here with a sigma w, which then gives the kind of the amplitude of this turbulent motion. So this gives really the amplitude of these turbulent motions. And this is a memory term. If you have a large eddy, Then you have a large memory, and the air is moving up, and will remember that it's still in a large eddy for some time before it's encountering a next eddy. So what you have to do is, if you follow a single particle, which is shown here, and the most important thing is that if you do that in the boundary layer, there your boundary layer turbulence is of course very important. So you have the mean flow here, and in addition, so this individual particle is one of maybe 50,000 particles that we simulate, and then this is following the mean flow, but at the same time some random fluctuation with a memory, with this time scale. And so it's moving up and down. It's also reflected at the top of the boundary layer and also at the surface. And so you need a turbulence scheme which pre-computes these factors, which give you the sigma, so the amplitude of the turbulence, and also the Lagrangian time scale. And so in the FLEXPART model that we are using, it's using a Hanna scheme, or described by Hanna 1985. So here's for an unstable boundary layer, here for a stable boundary layer. In the unstable case, you see that the amplitude is maximizing a little bit above the surface and then decreasing towards the top of the boundary layer. So the largest turbulence is around here. But then the time scale is increasing, from the bottom to the top, because at the surface you can have only small eddies due to geometry, whereas at the top of the boundary layer, eddies get larger and you have a larger memory in the system. And the stable case looks quite different. Well, that said, here one view a short comparison between trajectory models and LPDMs. I don't need to say too much again anymore. But what you see here is that sometimes a trajectory model, which gives a qualitative correct picture, this is what we simulate with the LPDM for the same case. And here is another case where the trajectory says there's a flow in the free troposphere towards Jungfraujoch. And if we look at the footprint calculated with our LPDM, it looks very different, because what the footprint is, it only shows us the contact of the air mass with the surface. And a lot of the air has remained in the free troposphere, and we see that branch also. But due to turbulent mixing, some of the air has moved down, and then most of the contact actually of the air that arrived at Jungfraujoch has been at a completely different place than this trajectory would suggest. So sometimes the trajectory can give a good indication, sometimes they can be quite wrong. And that's why we rather like to use these LPDMs. So then we use an LPDM to do source attribution and quantification. So basically we take measurements, combine it with atmospheric transport modeling, and I will show two things. First, a more qualitative method to attribute or allocate the sources in a qualitative way. We do that in a Swiss project for our government, and it's nice. We have 50 different species that we measure at Jungfraujoch with this system, and with that we can very quickly generate figures and some analysis. And then we also use quantitative estimation by inverse methods, which I will show later. So first, a few words about the measurements. And I'm first focusing on halocarbon measurements. And in Europe, we have a small network of halocarbon measurement stations, Macehead in Ireland, Jungfraujoch, and Montecimone in the Italian Apennines. And the species that we measure is, on one hand, we measure Montreal Protocol species, so species harmful to the ozone layer, like the CFCs, halones, solvents, halogenated solvents, methyl bromide, and also HCFCs, which are the hydrochlorofluorocarbons. So in these species, one of the chlorine has been replaced by a hydrogen, so that the OH radical can attack the species, and they are depleted already in the ozone and in the troposphere. So they are much shorter lived and therefore less harmful, but still they are also regulated under the Montreal Protocol. And then there's the second generation of replacement compounds, the HFCs, which don't contain any chlorine anymore. They are not harmful to the ozone layer anymore. But like the CFCs, they are often strong greenhouse gases. So they are regulated under under the Kyoto Protocol, and they're also the same category perfluorocarbons like carbon tetrachloride and SF6. And then we also measure, in addition to that, we measure, all is measured every 2 hours. We will measure a range of hydrocarbons, normal hydrocarbons in the range of C2 to C7, and a large set of other chlorine, bromine, iodine containing species, often short-lived, often with large natural sources like chloroform. And then also some new compounds. The industry always invents new compounds like these HFCs down here. This is a very interesting species. For instance, this is a hydrofluoroolefin. So it has a double bond and is also shorter lived, only a few days. And this has been suggested by the industry to be used in all the car air conditioning systems to replace HFC 134, which is used today. But there's only few models in the US which are using this so far. There's a big debate about the species, especially the safety in the cars. In the cars, Daimler-Benz doesn't want to introduce it. So this is still, it should be used in all new models, also in Europe, but it isn't. Okay, so halocarbon measurements, a few figures. This is some measurements at the different sites within Europe. So here, for instance, you see the different colors are the 4 different stations. Also New-Ålesund at Spitsbergen, very far north. At Spitsbergen, we are so far away from the sources that it's basically very flat, the curve. But let's focus first on the CFCs. You see, because of the ban, due to the Montreal Protocol, that all the CFCs are on the decline. Here is F12, and you see that we have quite noisy measurements up to 2008, and there we introduced this new MEDUSA system. Since then, we have a much better precision, and we can also measure many more species. Well, then here is F11, F113, so they are all decreasing, which is nice, because they're also strong greenhouse gases. And then, but here you see the replacement compounds. So today, instead of CFCs, we are using HFCs, chlorine-free species, and you see that they are increasing strongly. And we see at all the, we see on one hand that all the sites have a common background, but we see a lot of these spikes, so pollution events arriving at the sites, also at Jungfraujoch, which is considered to be at 3,600 meters high free tropospheric background, but we see a lot of pollution events also there. And you also see that HFC 125 is not only increasing, but also the increase is increasing. So here, 2 more species, HFC 152A with a short lifetime of 1.4 years. Therefore, you see some seasonal variation in this, but also many spikes. And here, HCFC 141B, this is the first generation of replacement compounds, so it still contains chlorine, and therefore it has been banned. And you see that the magnitude of the peaks is decreasing with time, because in the industrialized countries, it's not allowed to use it anymore. But the interesting thing is that after the strong increase here, it has leveled off due to this ban in industrialized countries, but then it has increased again, because it's so kind of the use has been shifted from industrialized countries to developing countries like China, where it's, I think the phase out is only by 2030 of this species. So that's the kind of measurements that we take. And now, how do we allocate sources of these species? And one really simple method is this so-called trajectory statistics method, which I think was first suggested by Peter Seibert and then refined by Andreas Stohl. So what you do is you have a time series of measurements, concentrations, for instance, methane. Then we determine a background level and the deviation, so the enhancement above that background due to a pollution event, transport from the boundary layer. And then for each measurement, we do backward trajectory calculation and assign that concentration above background to each grid cell of a prescribed grid where the trajectory hits, is within the boundary layer. So there we think when it's in the boundary layer, it has likely picked up emissions. In the end, you get a qualitative map of the distribution. So what that means is whenever the air is coming from that region here to Jungfraujoch, the enhancement that we measure at Jungfraujoch is something like 1.5 ppt or ppb, depending on the species above background. What we have done is recently we have changed this a little bit. To one hand, we are not using trajectories, but the footprints from the Lagrangian Particle Dispersion Model, so the map of the surface contact of the air. And we're also using an iterative approach. So instead of estimating concentrations now, we get maps really in units of emission fluxes. But we still caution that this is not a full inversion, but it's still a qualitative thing. No.
Means you have trajectory on one hand, and some people do like you have the site and you consider 1 degree by 1 degree box, calculate trajectory at 4 points, and if the trajectories are not coherent, don't use them. So what is the advantage of using the LDPM footprints over this trajectory method?
When we apply exactly the same methods, replacing the trajectories by footprints, we get fairly similar results, surprisingly, because the LPDM really also accounts for turbulent transport and also convective transport, which the trajectories in our case don't. So you would think that it makes a major difference, but the real difference is that with the LPDM we can make really a quantitative estimate. It gives us really a quantitative estimate of the sensitivity of our sampled air to emissions upstream of the measurement site, which with a trajectory model you can only maybe say when it's in the boundary layer, but you never get a really nice quantitative picture. But for qualitative mapping, it gives fairly similar results. But yeah, maybe I can explain maybe also later a little bit more. But sometimes it's a bit disappointing that we're calculating 50,000 air parcels instead of one, that the differences are not so much bigger.
Yeah, that's what I was thinking, that you are using, it is computationally expensive,
yeah.
And if it is not improving the picture, then
yeah, it's improving, but not tremendously. Yeah. Not in such a significant way that as we were hoping. But okay, but the trajectory statistics method as applied, as I explained now, with LPDM, not with trajectories. That's the kind of pictures that we generate for our ministry. They want to know where in Europe are the sources of these different components. So for HFC 134A is the cooling agent used in air conditioning in cars. This is often used in stationary refrigeration. This is a foam blowing agent used in, for instance, window insulations. This is also a foam blowing agent. And we see here the distribution of the sources, qualitative, for the year 2004 to 2006. So it's always 3 years averages, and this for the latest years, 2010 to 2012. You see a little bit the evolution. HFC 134A, the sources don't change very dramatically, and also the distribution. So we see high emissions here in northern Italy, and then also in Germany, the Ruhr area, Benelux regions. If you look at this 125A, which I showed before, that its increase is increasing, we see that really also that in these pictures that especially here in the latest years in southern Europe, obviously the emissions have increased quite substantially of this species. Then 152A is interesting because it has, even if you go further back in time, it has been used mainly in Germany, but this use has completely shifted to the south, and now it's almost exclusively used in Italy. And Italy, in fact, declares 0 emissions of this compound. And here, that's also interesting. This species is only used in Europe, and it's only produced in this factory at this location where this circle is. So we think that the patterns that we see here, these plume patterns, is actually due to emissions from that factory, and our method is not able to correctly allocate really the source. It cannot produce a point source, but rather like a plume downstream of that factory. Yeah.
Yeah, I remember the potential source contribution method, which also uses the trajectory to identify the source regions, and they use a kind of weighting functions. Means like if you have a trajectory coming from a grid,
yeah,
and you have only single point, and that is high, so they assign it a factor. So means by probability that the contribution of that grid cell should be 1.
Yeah.
But since, and there is another grid point from where the trajectory is coming 6 times, and 3 times the value is higher.
Yeah.
So it will give a probability of 0.5. So how do you rule out this kind of possibility here?
Well, I think this is working very similar to this PSS method. And we are actually applying an iterative step that first we make a first map, and then instead of distributing the concentration all over the footprint as a constant, we take the distribution that we estimate in the previous iteration. And that allows us to further constrain individual point sources. But I do this very conservatively, this iteration, because it also enhances the noise. So there's a danger that it shows that some features are popping up which are not really realistic. Because there's always the problem, this is not constrained by some a priori or something. That's, I think, a major problem. Yeah.
Especially in your first 2 columns, it looks like there's a minimum in the 2007-2009 period. Is that the result of the economic downturn?
I was also wondering. No, I don't think so. I think it's really a problem maybe of the statistics of the number of plume events that we have, and sometimes plume events where maybe the transport is not very exactly modeled. I doubt that this you see it in all species, kind of, or in most species, that it's like a decrease and then an increase again. I think that's really an artifact of the method. And you should always remember that we do this only with 1 single station. So I haven't included Macehead. That's the next thing that we really should do, also Macehead, and maybe Montecimone, to get a better picture. So we try to estimate the distribution over Europe just for 1 station, which is a little bit risky. Here a few other species, HCFCE, which has been banned, and you see very nicely that in the latest years there are almost no emissions anymore. This is a pesticide which has been used in strawberry plantations, vegetable plantations in Spain and Italy, and it has also been banned and completely vanished, which is interesting because it also has substantial natural sources, methyl bromide, but we don't see anything of that. So the anthropogenic has been very strongly dominating in this region. Well, then here 2 solvents using for textile cleaning or chemical and pharmaceutical industry, which have also decreased with time mostly. Okay, that's maybe the last thing that I would like to show is this HFC-23, because this is particularly interesting. This is a very strong greenhouse gas, has a GWP of 14,800 on the 100-year time scale, and it's a byproduct of the production of HCFC-22, and this is a compound which is used in the production of Teflon. And this is, of course, because it's such a high GWP and regulated under the Montreal Protocol. And this is the map that we see in these both periods. We see strong sources here over northern Italy. And we know that there's a factory producing Teflon. Well, okay, first then we made an analysis based really on an inversion study published in 2011. And we say that we estimated that Italy releases 26 to 56 tons per year of this compound, but Italy reports to UNFCCC only less than 10% of that, 2.6 tons per year. So, and this is the company Spinetta Marengo, which is one of a few Teflon production factories in Europe. It's located more or less at that spot. And we got a lot of response on that publication in the media, here French newspaper, Swiss newspaper, Italian newspaper Corriere della Sera said Switzerland is accusing Italy. So the newspapers liked this story more than Nature, unfortunately. Okay, so this, just to show you that we are really confident that it's that factory here, I made a small animation. And up here you see the time series of HFC-23 with all these individual peaks. And here you see a single footprint, so the contact of the air with the surface before it arrived at Jungfraujoch. And I can animate this, oops, hopefully. So you now see, here we have contact with the south, and then we had the plume, and it's moving forward. And actually, usually when nothing is happening, then the air is coming from somewhere, but I can also move a little bit, for instance, to this peak here. And then you see quite nicely that during that plume that we have this transport from the south, from the area of that factory. And if I move even further, here maybe the largest peak here at the end is also nice. So before that we have advection from all over the place, and then as soon as we enter this peak, we have this like a highway from the south. Air is coming from the north, turning cyclonic way over the Gulf of Genoa, over that factory, and then transported to Jungfraujoch. So that's so much about halocarbons. And how much am I in time so far? Huh? Half an hour?
About 35 minutes.
Okay. So the next thing is, this was a qualitative picture, but we do also inverse modeling where we really want to quantify the emissions on a solid basis, and we do apply two different methods, kind of a classical Bayesian estimation where you try to minimize this cost function, which has this modeled observation misfit, and also the deviation from an a priori. So you have an a priori emission from an emission inventory, for instance, and you're just looking for a solution X, which would be your emission distribution, which should not be too far away from your a priori. But at the same time, you're looking for an X, which, when you project it onto the observation points, should also not be too far away from the observations. And each part here is weighted by a covariance matrix giving the error uncertainties. So the uncertainties, how much do you trust your observations, how large are the errors in the observations, and how large are the errors in your model. And here is also a covariance matrix which gives the uncertainties in your a priori. So if you trust your a priori a lot, then this has a large contribution to this term, and you will not be able to move too far away from the a priori. But you have a lot of faith in your model and the observations, then your solution is pulled much more towards the observations and farther away from the a priori. And we've done this in several studies for Europe and also for China. We have made 2 studies estimating halocarbon emissions in China. And then I've also developed another method where more a sequential assimilation using a Kalman filter. So you start with an analysis for the time step k minus 1. So this would be the emission distribution at time k minus 1. And now you need a dynamical model which predicts, forecasts, let's say for the next day, what would be the emissions be on the next day. And you see this is a very simple model. It's a persistence model, so I assume the next day the emissions are still the same as today, except for an error term which allows that the solution is more slowly drifting away. And drifting away because the observations are pulling it towards a certain direction. And here is the Kalman filter step. So I had this, now from this analysis, I get this forecast for time k. And then I correct this forecast by using the observations and compare the observations with my model simulated values and apply this Kalman gain matrix to that so that the forecast will be modified in such a way that the differences between the observations and the model simulated values will get smaller. And like similar to here, you have in this Kalman gain matrix, you have different covariance matrices giving different weights to the different components of the system. And you have such equations also for the covariance matrices. So not only the solution, but also the covariances are moved along. Yeah?
what is the unity of your observation? Is it the fluxes? Is it a flux or a mixing ratio?
The observations?
Yeah. What is your state vector here? I mean your observation.
Yes.
Is it a flux?
It's a concentration.
It's a concentration,
Yeah.
and you constrain the fluxes with a concentration.
Yes.
So, okay. So how you specify your covariance matrix between the concentration and the flux? Because you expect to constrain the fluxes with a concentration.
Yes.
Okay.
Yeah.
So.
So you have an error covariance matrix for the model data mismatch. So what you typically do, you take a diagonal matrix. You say that my model, well, I have errors in the observations, but I also have error in my model simulation, which explains the observation, and that's the dominant error. So you combine these components, the precision of the measurement with the uncertainty from the model. And the uncertainty from the model you can estimate, approximate with a first forward simulation with the a priori. But then we do iteration and estimate again. So, but really the details, how we construct these, it's a little bit more advanced than what I say, because we describe our covariance matrix by a few parametric terms, which we estimate with a maximum log likelihood method. So we run the systems many times and try to maximize the log likelihood for those parameters. So we have the components, the observations, time series here, and the state vector here. So it's actually composed of several components. I have here the emission, but I also have the background concentrations at the individual stations as a component of the state vector. So I'm also estimating the background because, yeah, and then some other terms which I will not really go into. And so you have an observation operator. You get an estimate of the concentration that's observed by applying this observation operator onto the state vector x, and it actually has two components which are shown here. So if you have an observation here, you can describe it as composed of a background concentration. That's this term here, the background, which we also estimate by the Kalman filter, and then the contribution from recent emissions, regional emissions, which are simulated with FLEXPART. So that's the emissions multiplied by the footprint computed with the FLEXPART. It gives you the concentration. Footprint is the sensitivity to the sources times the sources is the concentration or the mixing ratio. And this is so for a single time step, the footprint or this matrix F would look like this. And I have here observations would include observations from Macehead and from Jungfraujoch at the same time. Or in matrix form, it would look like this. So instead of solving, we use a reduced grid because this has a lot of terms, so that's a very heavy inversion problem. So we try to reduce the inversion problem, therefore reduce the dimension of the grid. And by accounting for the fact that in the vicinity of our observation site, we have a lot of information, but further away that the information content decreases. So close to Jungfraujoch and Macehead, we have small grid cells, and further away, we have larger grid cells that we estimate. Well, here's just an illustration. We've done some idealized tests with an idealized traces. And when we start with a completely uniform initial distribution of emissions, we say we don't know anything. And then we simulated artificially the concentrations at Jungfraujoch and Macehead and adding some noise and seasonal cycles of emissions or things like that. Various experiments you can read in my paper. And then what will happen, it will slowly change. This is, by the way, the real solution because in these idealized experiments, we know what the solution should be. And after 1 month of assimilating these artificial observations, it looks like this. After 2-3 months like that. And after 5 years, we are very close to the original. So we need really a lot of measurements to constrain the emissions in this area. But then, yeah, we get close to the solution. And this is actually done with realistic uncertainties of the model uncertainties. If I would decrease that uncertainty, the conversion to the solution would be much, much faster. But, okay, here's just to show you that the system works really nicely. So the blue line is the background that is estimated with this Kalman filter, and the red lines are the concentrations that we estimate, and the black lines are the simulated values. And subtracting the background, we still have, so just the deviations from the background of our model simulated value has a correlation of 0.83 with the measurement. And here at Macehead, even 0.87. So we can, and if you zoom in just in some area, you can see here that our model simulation can trace the measure concentrations really very, very closely. So we have a good faith that our model is doing something reasonable, and then we can estimate emissions here. But I think I will skip that figure. This is just the red bars are was reported values to UNFCCC for, let's say, for instance, for Germany. That's the value reported by Germany for the year 2009. And this is our simulated concentration for 2006, 7, 8, 9, and 10. So here we have a relatively good match between the reported values and our estimates, and sometimes we have larger deviations, Spain, Portugal, and Ireland. Ireland is also known by, has been also identified by others that they are strongly underestimating their emissions. You can also compute on a per person basis that it's very unrealistic what Ireland is reporting. So the last part, do I have some 10 minutes? Okay, so now I'm going to the regional scale, and then I would like to, yeah, we have worked a lot on this regional model, mesoscale version of FLEXPART. So we coupled FLEXPART to the mesoscale numerical weather prediction model COSMO, and you see what we do. Typically, we do simulate the transport first at 2 kilometer resolution, or with a numerical weather forecast model with this resolution. And once the particles move out of this domain, we continue with input from 7 kilometer resolution numerical model. And then we can even go globally to ECWMF and transport on the globe. So we do nested simulations with FLEXPART. And the special thing of this version of FLEXPART is which is the only version which directly uses the internal coordinate system of the model. All other versions of FLEXPART, ECWMF, GFS, CHEM, they do have to interpolate from the model grid of the driving model to the internal grid of FLEXPART. And we have replaced this by directly the grid of COSMO. So we had to more or less rewrite the code quite a bit. And we've parallelized the model code and ported to it. Yeah, many things. So we have applied this to aircraft observations over Switzerland, but I think I will skip this a little bit in the interest of time. And we've developed emission inventories for, you need a priori emissions if you do inversion modeling. But I will focus the last part of this talk on this project, CarboCount, which we started about 1 year ago. It is a joint project with 6 partners within Switzerland, and so it's funded by the Swiss National Science Foundation. The main goal is to understand methane and CO2 fluxes in Europe and its sensitivity to climate variation. So that's one of our goals. And the second is that we want to set up a modeling and observation system of CO2 and methane fluxes in Switzerland. So a kind of a flux monitoring system, which also is like ICOS in Europe. I guess in the US you have similar attempts. So the observation network that we have set up last year looks like this. These red points are the new sites. We have a small tower here on Lagon, which my PhD student is responsible for. Beromünster, which is the main responsibility of the University of Bern. Gimitz, and this is really a tall tower. And then also Frühbühl, which is also a FluxNet site. So we have one site where we have concentration measurements and also flux measurements at the same place. And there's a range of other measurement sites, so for the Jungfraujoch and other locations where CO2 and methane, or either CO2 or methane are measured. So and this is, as you can see, the tower in Beromünster, 212 meter high, and we measure at 5 different elevations along the tower the concentrations of CO, CO2, methane, and from time to time also 14C samples. Then along with that modeling measurements network, we are far with the measurement network. It's basically complete. But with the modeling system we are still setting up, it's all again centered around COSMO. And COSMO is one of the, it's a model used by many weather services in Europe. The German weather service, Swiss, Italian, Poland, Romania, Russia are using or co-developing COSMO. And we have done several extensions to COSMO. So we implemented a tracer transport scheme, which is now getting into the official code of COSMO. In COSMO version 5, we'll have included this scheme, and also all hydrometeors will be transported in that way. And then we have developed emission inventories, high-resolution emission inventories at 500-meter resolution for Switzerland, for CO2 and methane with many different layers. So we can differentiate 46 different sources of CO2 in Switzerland. And then we have also, or we're still doing, this coupling of COSMO to the NCAR community land model, which will give us this natural CO2 fluxes, the exchange between the atmosphere and the surface. And such a coupled system, COSMO community land model, has already been developed a few years ago by ETH group, but they were not interested in CO2, but just from hydrology and climate simulations, regional climate simulations. So the new thing will be that we'll now turn on this biogeochemistry and the carbon cycling inside CLM. And here, just for the last thing, it's just some to give you some flavor of the capability of our model, of the transport model. This I just received a few days ago from my PhD students. So this is now measurements at Beromünster at 12 meter at this lowest elevation. The red is the measurement, and the blue is our model. And this is from early December to late March. So it's basically a winter period, the last winter. And you can see that we can relatively nicely trace this periods of enhanced concentrations in CO2 and also CO and methane. And if you go higher in altitude, you see the following, that the concentrations in the measurements, but also in the model, they're going down. So during winter, you have quite a strong layering. And so we are quite happy that the model is doing something nice, that if we release the particle at a high level, that we also really simulate lower concentrations, that the footprints that there's less contact with the surface emissions. I can play back and forth this. It's also interesting to see that, if you plot CO and CO2 together, you will see that there's an extremely high correlation between CO and CO2. So in this winter period, it seems that almost all of the CO2 is anthropogenic, that it looks like. So we will see in summer it will certainly be different, but it's surprisingly high correlation during winter between CO and CO2. And methane is a little bit different, has very different sources. It's mainly 80% is ruminant in Switzerland emissions. But we also see some problem. For instance, if you look at this peak here, we see in the measurements, if you go to the highest levels, we still have rather high concentrations, almost as high as at the surface. So it seems that on that day, it was a relatively well-mixed atmosphere, whereas our model, as you can see, the blue curve here, starts also at high levels at the surface, but if we go higher, the concentrations decrease too much. So we have a too strong layering in our model. So I think from this kind of measurements along the tower, we will certainly learn a lot about the mixing in our COSMO model, and maybe we can do something to improve that. Although it's the weather model component which we don't have a good handle on to improve that, but we'll see. But we are very I'm very happy with these first results, I have to say. I was much more skeptical. Yeah.
Yeah, but I can see a lot of difference in the absolute values between model and measurements. It has to do something with the
Where do
emission
you see
telemetry?
that?
The measured values are on the right side.
Oh, okay.
Yeah.
Well, okay. I forgot to say. Of course, what we simulate, we simulate only the transport during the last 3 days. So what we can simulate is only what has been picked up during the last 3 days. And this is responsible for most of the variability in the measurement. Whereas the rest is kind of the large-scale background. So if we go back maybe 4 or 5 days, maybe we will be able to trace a little bit more of the variability even. But here we made a very simple first estimate that we just take a constant background in the measurement. We say that's a large-scale background, and then then these are just the deviations, the enhancement above the background due to emissions during the last 3 days, because that's the only thing that we model. But you can imagine here for CO, I think you see already the problem that here towards the end we see a larger deviation between the CO measurement and the model, because we always keep the background constant, whereas of course CO has quite some seasonal cycle. So I'm sure that we can still quite a bit improve on this very first simple approach of taking a constant background. Because we can also take a background from a global model, taking the particle dumps at the end of the simulations, we can interpolate from a global model onto the end point of the backward simulation, which would give us the initial concentration that the air parcel has before it's advected over these 3 days towards the station. But we haven't done that yet in this case. Okay, so that's my conclusions. I hope I could convince you that Lagrangian particle dispersion models are powerful tools to study especially long-lived and weakly reactive trace gases. For reactive trace gases, it's a bit tricky. Time-inverted simulations are very cheap. It's from in the Eulerian model, building an adjoint model is something very tedious, but so some people have called this Lagrangian model as self-adjoint, because you just need to turn the sign of the advection term, and then you get the backward simulation. We use these qualitative trajectory statistics. We still use it because it's very quickly we can do it quickly and apply it easily to all the 50 compounds that we measure. And it gives some nice first ideas about the source regions and how the emissions change with time. It's for illustrative purposes, it's really nice. I think that the HFC23 story had a big response in the news, and I think it clearly demonstrates that we need independent top-down verification. And the European Environment Agency is frequently using this case to really make that point. So they were very happy about this study. And the FLEXPART-COSMO model we developed for simulations down to the resolution of a kilometer scale for regional studies, and we have applied this for methane observations from aircraft, which I skipped in this talk, but also we are using now in CarboCount, and I think the first results are quite promising, and we hope that we can really use this system finally to estimate the fluxes in Switzerland. I think that maybe the last word, in the past, these inversion studies on carbon, CO2, and so on, they have always focused on background stations, really remote stations, and then there's a clear trend to using these measurement sites closer to the sources, but that requires that you have a high-resolution model capable of simulating that, because now you're interested in what before has been noise and been thrown away, because you say pollution events we cannot represent with our global models. Now we do exactly the opposite. We just take these pollution events to estimate sources. And I think that's a nice step forward. Okay, thank you.
Are there any further questions?
kept my questions to the end. I have 3 questions, in fact. Have you considered using FLEXPART-COSMO labs, using ensemble prediction for the meteorological part?
No, that's a good. You know that system, yeah?
Well, I heard about it.
No,
but because you mentioned the fact that you are relying on the COSMO, and we know that there may be rather uncertainty in the mean field.
Well, another group at ETH will do ensemble Kalman filtering for their inversion, but for the moment not using different meteorological forecasts, but just changing the fluxes and do ensemble simulations with different fluxes. But it's a very good point. But at the moment we don't think we will use that. But that could be very powerful in the future.
And the other question is, have you considered other turbulence profiles other than HANA's? For instance, could the COSMO provide information about that?
Yes, COSMO has a prognostic TKE scheme, and we were already thinking of because we had previously another dispersion model which was using this TKE to calculate the turbulence, and we will probably implement it as well to make a comparison, but so far we just have this HANA scheme, which is the standard scheme inside FLEXPART. But something we have added, we have implemented another convection scheme. Before there was just only the Emmanuel scheme in FLEXPART. Now we have also the Tietke scheme, which is more consistent with COSMO because it's the same scheme that's also used in COSMO. So we use the same scheme now in our FLEXPART transport as well.
And the last question, I might have missed it, but in the long time simulations that you showed at the beginning, a couple of years, what was the input for the mean wind, for the mean meteorological data there?
The meteorological data was ECWMF at 20 kilometers resolution.
So analysis?
Analysis, yeah.
Mm-hmm. Okay.
But actually, yeah, we also use COSMO at 7 kilometer resolution, and it's very consistent. It's surprisingly consistent, the ECWMF 20 or COSMO 7. Even if it's different resolutions and different models, but if you do trajectories with either one and do this kind of maps, they look very, very similar. Yeah, they're always the same, yeah. Yeah, that would. We know that our COSMO model is overestimating boundary layer heights. I think that's the main problem that we have at the moment. And I don't know how to solve that.
If there are no more questions, I thank you very much. Thank you, Dominik, again. And Dominik is here today in FL0 if you want to talk to him any further.
Thank you.